Hello everyone, I'm Kao Chow from the University of Hong Kong. Today I'm very excited to share my recent work about protecting privacy against unauthorized face recognition. And this is a joint work with my collaborators from Georgia Tech. Face recognition has many life-enriching applications, and deploying a face recognition or FR system is easier than you can imagine. You don't need to even train your own machine learning model in the whole process. The most important ingredient is a reference database. This database should contain at least one image for each person you want to recognize. The second ingredient, of course, is the FR model. This is supposed to be the most difficult to obtain, but in fact, you can just download any pre-trained model from the internet. This is because modern FR models, they are not classifiers. They can be used to recognize any person even if they were not included in their training process. The way it works is that you just need to send in each reference image to the model, and the model will project it onto a low-dimensional space. What those pre-trained models can do is make sure those images of the same person will collocate in the embedding space, and those of different people will just form their own clusters. Then when you have an image of an unknown identity, you can simply reuse the same FR model to extract the corresponding embedding and then look for nearby images with a known identity. This property in face recognition lowers the bar for anyone to build an FR system, as long as a reference database can be constructed. Misuse or abuse of this kind of models can lead to serious privacy concerns because privacy intruders can construct this reference database by web scraping. In fact, a couple of companies have already done it on a large scale, having reference databases with images of millions of citizens and offering face recognition services without their consent. To combat unauthorized FR, we need techniques that allow us to protect ourselves proactively, and this is where anti-FR solutions come into the picture. Before sharing our photos online, we can pass them to an anti-FR solution to pre-process them, such that when they are out there, may be scraped by privacy intruders to enrich their reference database, they will not be useful. A query image will not be matched to the correct reference images. To be qualified as a useful anti-FR solution, it must be effective, especially when we don't know which FR model will be used by the privacy intruder. Also, we don't want to wait for a long time before sharing our photos online, so it has to be fast. Finally, of course, we want to ensure the protected photos look nice. No one wants to share photos with the face being seriously distorted to avoid face recognition. With all these requirements in mind, we introduce an anti-FR solution called PMask. The key idea is to design an optimization approach that iteratively learns a privacy mask, introducing small changes to the facial image to be protected such that the extracted embedding will not collocate with the clean facial images of the same person. The iterative process should have a clear termination condition to avoid unnecessary perturbations, degrading the visual quality, and also to save time. The learning should emphasize the generalizability to different FR models because we have no prior assumption about which model will be used by the privacy intruder. So given a photo to be shared, we first use existing face detection techniques to crop the regions containing a face. Then each face will be processed independently by PMask to learn and apply nearly imperceptible changes to it. Then we put these protected faces back into the original photo, and the user can now share it online. In the next few slides, I will highlight the key components in PMask, and I will start with how we optimize the privacy mask for a given facial image. We assume that some images of the user are available for PMask to help protect their privacy, and we have access to a reference database of other people, which can just be a public FR dataset. Given a facial image to be protected, we first randomly initialize a privacy mask and applied it to the original image to generate the protected version. This privacy mask will be iteratively optimized. The way it gets optimized is that given a known FR model, we require the privacy mask to protect the facial image by pushing it in the embedding space towards the direction of the closest facial image of a different person. And it must overshoot by a margin. This is captured by the first term in the objective function. The second part is to ensure image quality. We require that the protected image should be visually similar to the unprotected one. For that, we use structural similarity or SSIM to measure the differences between two images. The user can specify a budget for quality degradation, depending on their privacy requirement. Both of these plots have a clear termination condition, so once the conditions are met, the protection is done. This is different from many existing approaches. They tend to conservatively set a large number of iterations to maximize the chance of successful protection. So far, I have talked about how to protect against a given FR model. However, our goal is to be effective against unknown ones, because we don't know which one will be used. Here, we use an ensemble approach with joint optimization. The key challenge is which FR models should we choose to form a team, so that synergy can make the privacy mask effective against other models not in the team. To show you the importance of forming a good team, here on the left is a small collection of publicly available FR models. We enumerate all two-member combinations and measure how well each team delivers privacy protection, which is the failure rate of FR reported in percentages. On the right, we can observe that some teams perform much better than the others. If you make a poor choice, the protection can be 60% less effective. But how to find this subset of models in a scalable manner is an important question. We can't just enumerate all of them, do some measurements, and see which one is better, because it can take forever. To overcome this challenge, we introduce a diversity-driven technique for FR teaming. The idea is that if PMask is generated to protect against very different FR models, then it is more likely that it will also be effective in some other FR models unknown to us. To find out those different FR models, we use error diversity. In particular, for each FR model in the collection, we use a public dataset to find out those facial images where the model makes mistakes. Then, given a team size, for example decided according to the resource limit, we can enumerate all possible combinations and calculate how much the team members disagree with each other when they make mistakes. Intuitively, we want a team that all members make mistakes differently, and this reflects their diverse internal mechanisms in recognizing faces. The team making the most diverse mistakes will be recommended to generate the privacy mask. We have conducted extensive experiments on FaceScrub, a popular FR benchmark, and here we highlight the results. More details are available in our full paper. First of all, PMask can protect against FR models that are unknown during the protection. On the left, we have facial images of 3 celebrities as queries, and let's assume we don't know who they are. Consider the privacy intruder uses a ResNet50 model trained on a VGG face dataset for face recognition, and the privacy intruder tries to use this model with the reference database to find the most similar face to each of the query image. Before looking into the recognition result under protection by PMask, we can take a quick look at the protection by other existing schemes, including FOX, the first column, and TIPM, the second column. We can observe that under their protection, the privacy intruder's FR result still returns the images of the correct person. But under the protection by PMask, the third column, we successfully make the FR system to return an image of a different person. The same observation can be made when the privacy intruder uses some other FR models as well. Another thing to note is that if we look at those protected images by FOX and PIPIM, especially the second one, it is seriously distorted. But PMask can well preserve the visual quality of the protected images. For our FR teaming, we visualize the diversity score and the protection success rate for both 2-member teams and 3-member teams. we can observe that a higher diversity score indicates a better privacy protection. To give an example, for a two-member team, the average effectiveness across different models is about 93% when the most diverse team is used. But when the least diverse team is deployed, the privacy mask is only useful if the intruder used the same FR model, which is unlikely. Apart from the effectiveness, the teaming is also efficient because we don't need any test samples to generate some privacy mask and see which combinations of FR models produce the most effective mask. In summary, this paper introduced an anti-FR solution called PMask. The optimization of the privacy mask is convergence aware, so we can deliver better image quality and faster protection. We also introduced a diversity-driven FR teaming to strengthen the generalizability to some unknown FR models. That's all for this presentation. Thank you so much.